Um, this encompasses concepts of hypothesis testing, p-values, confidence intervals, their application and interpretation. At the end of the session, it is my hope that we should be able to, one, explain the concept of hypothesis testing as it relates to biomedical research, to identify the various types of statistical tests, not just for association, but for other purposes, and also to be able to select appropriate statistical tests for various scenarios. The third objective is to be able to interpret p-values, understand what they are, how they are interpreted, and to recognize their meanings and limitations. We'll also look at confidence intervals and highlight thereof. Just give me a minute. Apologies for that, sorry. So we look at confidence interval, what they are, highlight the role of confidence interval and how they're interpreted. And hopefully, at the end of it all, we should be in a position to apply best practices when reporting statistical results. So we'll start with the first objective, and we will consider this image, which we looked at last week, where the whole purpose of research is, at the end of it all, to be able to draw conclusions about population. Sorry, there's a little background noise. I'm trying to get it sorted. Um, but the whole purpose of this medical research is to be able to, at the end of it all, to draw conclusions about the larger population from which the sample was drawn. We all appreciate that it's difficult to study all populations because of many issues. So therefore, we usually study a sample. So a sample is a portion of the bigger population from which the sample is derived from. The aim usually is to draw a sample that is as representative as possible to the general population. And this is very important because you want a sample that is closely representative to the population from which it's drawn from, so that you are able to make generalizations later on in the during inferential statistics. So when you're conducting your study, it's important for you to consider sampling. Um, if you don't get your sampling right, definitely it's going to affect how you eventually translate the results you get from the sample back to the greater population. So that is the role of inferential statistics. So we study a representative sample and we draw conclusions about the population based on the information that we get from the sample. And this information that we get from the sample is what we described last week as statistics. So statistics are parameters that we derive from studying the sample, and we ask ourselves these parameters, these statistics, sorry, that we are looking at or we've derived from the sample, how do they relate to population parameters? Okay. For example, if you are to consider a study looking at mean blood pressure, average blood pressure of Kenyans, for example. It would be difficult to study the whole Kenyan population, but perhaps you can study a sample. Maybe you can consider a more appropriate sampling technique where every Kenyan region, for example, has an equal chance of being included in the study. Whatever we get from that sample that we're going to study will be statistics. So we'll get mean blood pressure of maybe 1,000 Kenyans. But then we want to use that mean blood pressure of 1,000 Kenyans to generalize and try to estimate a parameter now in the general population. Now, that process of estimating this parameter now in the general population from the sample statistic is what we refer to as inferential statistics. So what is the purpose of this inferential statistic? One is to infer, to be able to make out what this statistic would mean in the general population, to be able to predict outcomes from a smaller sample that you're studying and to be able to test hypotheses. And we shall look at what exactly these hypotheses are about a larger group. At the end of it all, the role of inferential statistics is to also enable us to account for uncertainty. Now, uncertainty usually comes in because in as much as you might employ the best practices in terms of sampling, there will always be variations of statistics. That is what you calculate within a sample from one sample to another. So if you are to consider the same study where you're looking at mean blood pressure of Kenyans, for example, you can have maybe 10 investigators, each investigator looking at 1,000 patients in various ways. If you're to do that same study, those 10 researchers, it's unlikely that they are going to arrive at exactly the same mean blood pressure. So there'll always be a variation from one sample to the other. And this is what we refer to as sampling error. That sampling error may be translated to the population in the form of uncertainty. And we're going to look at how exactly does inferential statistic take care of this issue of uncertainty when you're generalizing from a sample. So some basic concepts to perhaps get us started. The first one is there a difference between a population and sample? Yes, I think we've already highlighted the key differences and the rationale for studying a sample and not a population. Is there a difference between parameters and statistics? Yes. Sometimes people use them interchangeably, but they're quite different. Parameters are summary statistical summaries for population, numerical summaries for population. For example, if you are to talk about mean blood pressure of Kenyans, it's unlikely that there is a study looking at the whole Kenyan population. So therefore, parameters, by definition, since they are all population statistics, they are usually largely unknown. However, on the other hand, statistics is what is calculated from data, and this data is obtained from a sample. So at the level of the sample, what you obtain is just statistics. You can study 1,000 Kenyans and come up with a mean blood pressure of these 1,000 Kenyans. That mean blood pressure will be a statistic. And then we use that statistic to estimate the parameter, as in if you are to study the general Kenyan population, what would be the mean blood pressure? And we've already agreed that because samples vary, statistics will vary too. They vary because it's unlikely that we'll have a perfect way of sampling from the general population. So it's important for us to consider that because of the concept of sampling error, and we are going to look at how inferential statistics will help us account for these sampling errors. And how do we account for these sampling errors? We will talk about the concept of confidence intervals, p-values, what they mean, whether or not they actually quantify their uncertainty, or they just tell us something about the uncertainty without really quantifying it. So that is something we need to understand. So we've agreed that the role of inferential statistics is to estimate population parameters from what we measure in the sample. So we are essentially trying to draw general conclusions about the population from which the sample was obtained. Um, Inferential statistics have been described by various individuals over time. Perhaps the oldest and the most commonly used method of inferential statistics or framework of inferential statistics is what is referred to as the null hypothesis significance test, NHST. It's a method that was described at some point in 1937 thereabout by a British polymath who was also regarded largely as the pioneer of statistics. And it is one of the frameworks of inferential statistics that has been heavily employed in biomedical sciences, and that is what we're going to look at today. But it's also important to appreciate that there are other frameworks for inferential statistics, some of which we'll just mention because they've been um, given a mention in the sense that they might enable us to go around some limitations of null hypothesis significance testing. So we'll mention a few of those frameworks. So the null hypothesis significance testing is just a method of inferential statistics. So it was developed in 1934, refined over years. At the moment, it is undergoing quite heavy modification, so to speak. In the year 2019, the American Statistical Association dedicated a whole issue discussing this concept of null hypothesis significance testing and how it could be improved further. But we're just going to look at the conventional understanding of this null hypothesis significance testing. We're going to look at how it's currently implemented and interpreted, and some of the limitations and suggestions for improvement in terms of how it's supposed to be applied. So it's the most commonly used, but I've put in bracket misused, and we shall see how this concept of null hypothesis significance testing has been misused, so to speak. And we shall look at how you can go around some of the issues around this. So what is null hypothesis significance testing? So it combines two key concepts. One is to test the hypothesis, and we shall see what an hypothesis is. And then number two is to be able to use mathematics of probability to determine essentially the probability of observing this hypothesis, whether or not certain conditions are met. So there's also some mathematical computation that involves some probability statistics. So those are the two key concepts. So you come up with a hypothesis, you formulate it in a particular way. You set certain values that you're going to look at. You do the statistical test, you compute certain statistics, and whether they meet a certain threshold based on what you'll have calculated, the probabilities that you'll have calculated, then you either reject or fail to reject a hypothesis. So these are the two key concepts that we're going to dwell on today: hypothesis testing and probability theory. And the two main things in probability theory are actually just p-values and confidence intervals. So what are the key steps in hypothesis testing? So we at some point in this series we talked about coming up with a research question, and this is where hypothesis will come from. So what is a hypothesis? So hypothesis is often described as an educated guess by the researcher about a phenomenon in the population. Educated guess in the sense that there has to be some plausibility as to what you're proposing, either biological plausibility, statistical plausibility, so on and so forth. So it has to be an educated guess. Let's look at the scenario where we have an antihypertensive that has been used for the longest time, and we in the course of time encounter a new antihypertensive that is thought to be more efficacious in lowering the systolic blood pressure, for example. So you have an existing drug and a new drug. We are not sure about the efficacy, but because of the mechanism of action, then we think that the new drug may be more efficacious. So there is some sort of plausibility, and that's what makes it an educated guess. So when you're coming up with your hypothesis, it has to have some level of plausibility, some level of backing, scientific, biological, statistical, so on and so forth. So that educated guess also has to be precise, as in it has to be a very well constructed statement, not a vague statement, and it has to specify exactly what that researcher aims to test. And of course, it goes without saying that it has to be a testable statement, as in if this hypothesis has to be framed in a way that it can be tested through the scientific process. What does a hypothesis do? Essentially, it is a statement that proposes an explanation about a phenomenon. In this case, the hypothesis would be that the new drug could be more efficacious in lowering systolic blood pressure compared to the old drug based on certain plausible explanation. It's a precise, testable statement. I mean, we can have two groups of patients. Each group is given a different drug, and we can be able to measure their mean blood pressure. So it's a testable statement. It's also educated guess. So that is what a hypothesis is. Where do you derive the hypothesis from? Usually, in the scientific process, you start with a broad research topic. So the research topic could be cardiovascular diseases or hypertension, for example. In your reading, you might come across a research gap. The gap could be that there's a new drug that is thought to be more efficacious. It has been seen to work in other populations, but you could have a gap in the sense that it's a drug that has not been tested in our population. It could be that our population has a different receptor, for example, or just something that makes that drug to have plausibility in the sense that it could work better in our population, for example. So you could narrow down to that research question. Is the new drug more efficacious compared to the old drug in lowering the mean systolic blood pressure, for example? That would be perhaps your research question. And from your research question, then you derive the research hypothesis. So in the scientific process, it is expected that as you progress, you narrow down to a very specific research question and research hypothesis that can be tested. So this is the case that we are going to use throughout our discussion. So we have a researcher who wants to test if a new drug that is an antihypertensive reduces systolic blood pressure. Let's compare it to a placebo. Let's say it's just a new drug that has been developed. We first want to see whether it works relative to placebo before we introduce it to the market, where now we compare it with existing drugs. So you'll have two groups of patients, perhaps a randomized controlled trial. One group will be given the drug. The second group will be given a placebo. Then from this sample, so of course this is a sample, we get a statistic, and this statistic that we're going to derive would be a mean systolic blood pressure. Remember the measures of statistics that we mentioned last week, measures of central tendency and measures of dispersion. So here we have mean of 130 and a standard deviation of 10 in the drug group. In the placebo, they had a slightly higher mean systolic blood pressure of 135 with a standard deviation of 10. So pay attention to this case. We are going to use it throughout our discussion to understand what this whole concept of hypothesis testing is. So we started with a research topic, we came up with a research question, we narrowed down to a specific gap. From that research gap, the research question, we generated a hypothesis, we went to the field, we collected the data, and here we have the data. Then what do we do with the data? So the hypothesis for this case would be that perhaps the new antihypertensive reduces the systolic blood pressure compared to placebo, and this would have certain plausible explanations to back it up, right? So this hypothesis can be expressed in several ways. We have what we call the simple hypothesis, and that's what we just mentioned. So simple hypothesis is just a plain statement, essentially a plain statement of what it is that the researcher wants to go out and investigate, but still has to meet those criteria of a precise, educated guess that is testable. Often, this hypothesis would be expected to be expressed in two ways. We have what we refer to as the null hypothesis and the alternate hypothesis. So the simple hypothesis is then expressed in two ways, null and alternate. The difference is just how it's framed. Null, same as void, essentially just means that that hypothesis states that the new drug is in no way any different from placebo in terms of its effectiveness in lowering blood pressure. As in, what you're just saying is that you're negating possibility of there being a difference. That's why it's called a null hypothesis. So the null hypothesis for this case would be that there is no difference in the systolic blood pressure between those who are taking the new drug and those who are on placebo. The opposite to that would be that there is a difference, that those who are taking the new drug would have a lower blood pressure compared to placebo. So the positive way of putting this null hypothesis is what is referred to as the alternative hypothesis or the alternate hypothesis. So we're saying that patients taking the new the new blood pressure drug would have a lower systolic blood pressure compared to placebo. Now, I've put null hypothesis in green because the person who came up with the most widely used framework on inferential statistics developed that method based on the null hypothesis. So this whole concept of null hypothesis statistical testing looks at the null hypothesis, not the simple or the alternate hypothesis, just looks at the null hypothesis. So you are starting from a point where you are assuming that there is absolutely no difference between the two interventions. And then you try and build from there. So you're starting from a point where you are assuming there is no difference. So you're starting from a null point. That's why I've highlighted that null hypothesis. And that's what we'll carry throughout the presentation. So we started with a research question, research topic, research question. Now you have a null hypothesis that you've formulated and you've stated it in that manner. At the end of it all, the aim of hypothesis testing is to either reject that null hypothesis or fail to reject that null hypothesis. Now, rejecting null hypothesis means that there was actually a difference because the null hypothesis is stated in the null form, as in the no effect form. So rejecting a null hypothesis means that you actually observed a difference. We generally don't accept null hypothesis for reasons that we'll explain based on what exactly p-value means. We generally don't accept null hypothesis in the case when there is no difference. What we do is that we fail to reject because the null hypothesis significant testing is built upon rejecting the null hypothesis and not the opposite. The opposite, which is accepting the null hypothesis, is explored in a different framework that utilizes the alternate hypothesis, and that's not what we'll cover today. Today we'll just focus on null hypothesis significance testing. So at the end of it all, if indeed we find that there was a difference that is significant between placebo and the new antihypertensive drug, then we will reject that null hypothesis. If we find that there is actually no difference, then we will not reject the null hypothesis and the null hypothesis will stand. So that's another distinction I want us to get from the very beginning. We don't accept null hypothesis, we fail to reject null hypothesis. So why use the null hypothesis from Fisher's original description? He chose the null hypothesis, one, because it provides a baseline for comparison, because in his explanation, his reasoning was that without knowing the null, without knowing what no effect looks like, then how then do we judge a difference as being meaningful? So from his original description, he was comparing absence of effect vis-a-vis the observed effect to judge whether the observed effect was actually meaningful or not. For example, if the difference in the mean blood pressure is 5 millimeters, what does that 5 millimeters of mercury mean? Is it meaningful? And based on his original description, whether it's meaningful or not is tested relative to absence of effect. So that's why in his original seminal paper, he proposed utilization of null hypothesis rather than the alternate hypothesis where we assume that there was an effect in the first place. The alternate hypothesis was utilized, or rather has been utilized in a different framework that we'll just mention in passing. The other reason is, according to descriptions of these methods of null hypothesis significant testing, is that it enables us to evaluate or rather to quantify evidence. To quantify evidence in the sense that the effect we are seeing, is it because of a true effect of that drug, or is it just because of random variation or random error or by chance? Although I've put that in a question mark because as we explore this concept of null hypothesis significance testing, we'll actually appreciate that this method by Fisher does not really distinguish real drug effects from random variation. There'll always be random variation. What it just tells us is what we are observing in the case that the null hypothesis is true, that there was no effect, what is the probability of us just getting a significant difference, right? Whether by random error, by chance, or by due to real effects, for example, right? So there's always been a lot of controversy as to whether this null hypothesis actually quantifies evidence, because as we look at the definition of p-value, which is the central statistic when it comes to null hypothesis significance testing, it does not really quantify the evidence, right? It's just a threshold, so it does not really quantify evidence. So if you want to quantify evidence, then what route do we take? But the whole point I'm stressing here is why the null hypothesis. Why is it important in this hypothesis testing? So this is what is conventionally described as the key steps in hypothesis testing. So you start with your research topic, your research question, you define your hypothesis, either simple, but you have to state the null, which is very important and central in this process, and also the alternate hypothesis. From there, you choose a significance level, which we will discuss. What exactly is this significance level? You go ahead and collect and analyze the data. From the data, you calculate the statistic, that is from the sample itself. Based on that, and based on certain thresholds that we look at, if it meets that threshold, then you either reject, or if it doesn't meet that threshold, then you fail to reject that null hypothesis. So this is what we are going to look at. We've already defined what a null and alternate hypothesis is. Let's look at significance level. So we've stated our null hypothesis that there is no difference in the mean systolic blood pressure between those who are taking the new drug versus those who are taking placebo. So that is our null hypothesis. So what is this significance level that was proposed by Fisher? Significance level is what is sometimes also referred to as the alpha value. So what is it? It is what we use as a threshold for deciding whether to reject or fail to reject a null hypothesis. So we use it as a threshold. And we shall look at how exactly do you utilize this threshold. The problem with the significance level, and I know most of us are aware of the recommended threshold, which is 0.05. Most of us would set the significance level, sorry, at 0.05. Where did that 0.05 come from? Why is it used conventionally? That reference point or threshold of 0.05 to decide whether to reject or fail to reject a null hypothesis, or to enable us to identify significant, so to speak, results, was developed by Fisher, and it was purely a matter of convenience. And we shall look at why it was a matter of convenience. More importantly, is to appreciate that this significance level is set by the researcher. So you often, in your method section under statistical analysis plan, you have to declare the alpha value, as in you have to mention, before even conducting the research, what would you consider as a significant threshold beyond which you would consider the results are either significant or not significant. That is essentially what alpha level is. So it is set by the researcher before collecting or analyzing the data. Essentially what you are saying is, if you set an alpha value at 0.05, what you're just saying is that you're giving yourself an allowance, you're willing to accept a risk that you're going to declare that there was a difference when in the first place there was none. Declaring that there was a difference means that you rejected a null hypothesis, as in you actually say that there was a difference, when indeed that null hypothesis was true. So you declare the results or the drug to be effective while in the first place, there was no difference between the drug and placebo. This is what is referred to as a false positive, also referred to as a type 1 error. So the significance level often infers that this researcher is willing to accept up to perhaps a 5% risk that you're going to declare the results, or rather that drug to be effective while in the first place it is not effective. So therefore, if you find that whatever you compute is less than the 0.05, most researchers would declare that result to be significant, and therefore they will reject the null hypothesis. If that risk is greater than 0.05, then the researchers would usually reject the null hypothesis and declare the results as not significant. But this 0.05, we have to appreciate that it's just a threshold. It does not really quantify the magnitude of the result that we are getting. So where did it come from? So Ronald Fisher in 1934 in his seminal paper mentioned, or rather tried to come up with a reference point to help standardize the whole process of declaring results as to whether they are significant or not. In his paper, he argued that 0.05 would be a good cutoff to determine whether the effect is significant or not. Where did he get the 0.05 from? This is exactly what he said in his paper. He said that the value for which P is equals to 0.05 or 1 in 20 is nearly 2 standard deviations away from the mean. That was his statistical reasoning behind 0.05. What he mentioned was that this cutoff value is convenient to take at this point as a limit in judging whether a deviation is to be considered significant or not. Keyword there to underline is convenient. So it's what he proposed. He then went ahead to mention that it is open to the experimenter to be more or less exacting in respect to the smallness of the probability he would require, as in it is for the researcher to determine whether 0.05 is convenient for him or 0.01 or 0.001. So he suggested that it's just a convenient cutoff point, but as a researcher, it's up to you to determine which one would be more convenient to you. Why am I stressing this? Is so that we appreciate that this P of 0.05 was a rather arbitrary cutoff. And that is one of the arguments against it, in the sense that it has been utilized as the textbook cutoff, yet it was just an arbitrary cutoff. There are better ways of going around this, but this historical note is quite important for us to consider, even as we look at what exactly the correct way of interpreting the p-value is. So from the significance level, which is the alpha, then you go to the p-value. So the difference between significance level and the p-value is that significance level is declared before the results is collected or analyzed. And the person who sets the significance level is the researcher. P-value, on the other hand, means it's a probability value. It is what is calculated after analyzing the data. So in your mind, you set a threshold of 0.05. But what you actually get when you analyze the data in the sample is what is called the p-value. What is the original description of the p-value? And what is supposed to be the actual definition of p-value? So p-value just means if the null hypothesis were true, if there was no difference in the first place between the drug and placebo, what is the probability of you observing a difference? So as you can see, The p-value assumes that the null hypothesis is true. P-value assumes that there's no difference in the first place and goes ahead to tell you if there is no difference truly, what is the probability of you getting a difference anyway? And the reason why you could get a difference anyway, even if there's no true difference, could be due to random variation, could be due to chance, right? Could also be due to subtle differences that were not picked in the study. So it does not tell you the source of this difference that you can get when indeed there is no difference. It does not tell you where it comes from. It just tells you that in as much as you're saying that the null hypothesis, starting from the point where we are assuming that there is no difference, based on what you've calculated, there is still a chance that what you are seeing is due to random error or due to chance or due to something else. So it just tells you that probability. You then look at that probability against a threshold that you had set before. If it's above that threshold, then it means that what you are seeing could as well be due to chance or due to a random variation. If it's less, then it means that it's less likely to have been due to a variation or chance. So often you pair the alpha value and the p value, and we shall see how the two are used together. However, when describing this p-value, Fisher also put a note there. He said that no isolated experiment, however significant in itself, can suffice for the experimental demonstration of any natural phenomenon. As in, at the end of the day, even if you do that study and you compute the p-value against an alpha threshold, for example, in itself, it may not really suffice to explain a phenomenon that you're trying to explain, which means that there are other things that you'll also need to compute to fully explain the difference that you're seeing. P-value just tells you that there might be a difference. The difference may be significant, but it does not really tell you the magnitude of the difference, does not tell you the direction of the difference. So there are other aspects of the result that will not be captured by the p-value. So what we need to understand is that significance level and p-values are purely threshold. Once that p-value meets a certain threshold, then you decide whether to reject or not to reject the hypothesis, or whether to declare the results as significant or not significant. So just purely a threshold, but does not tell us what is the magnitude of the difference that we've seen. What is the direction of the difference that we've seen? Is it that the drug was more efficacious compared to placebo, or was it the other way around? Just tells us there's a difference. Does not tell us the direction or magnitude of the difference. So how are the two usually conventionally used? So usually you compare what you've computed, which is the p-value, vis-a-vis the threshold that you had set, which is the significance level. So often, if the p-value is less than the threshold that you had set, often you reject the null hypothesis. Null hypothesis being rejected means that you observed a significant difference. But if what you've computed, if that p-value that you've computed from the sample is greater than the threshold that you had set, which is the alpha, often most researchers would fail to reject the null hypothesis and therefore declare the results as not being significant. If you are to look at the graph on the right, this is a graphical representation of the results that you can get in a study. So for example, this is a plot of the set of possible results that you can get vis-a-vis the probability of observing that result. Towards the edges of this bell curve, you tend to have extreme observations, which most of the cases will be very unlikely observation. Now, if you look at this edge towards this point here, there is a line there. That line is the alpha, as in this is the threshold or the cutoff that the researcher usually sets. This area shaded in green is the observed p-value. This is what is computed from the sample. If this p-value is greater than the threshold, therefore it crosses over to this side, often most researchers would declare these results as insignificant because it's greater than the threshold you had set. It means that there is a huge chance that what you are seeing could just be due to random variation or by chance. But if what you've computed is less than the threshold that you had set, for example, P being less than alpha, which is 0.05, often most researchers would declare these results as significant and they'll therefore reject the null hypothesis. But is that really how the null hypothesis significance testing should be interpreted? Maybe, maybe not. At the end of the session, maybe we will have an idea. So we started with a research topic and a research question. From the question, we formulated our null hypothesis. We've chosen a significance level. So we've agreed that the conventionally used significance level alpha is 0.05. And we have understood the origin of the 0.05 from Fisher, the statistical basis being it is at least within 2 standard deviations away from the mean. But to remember that it's an arbitrary and conventional cutoff. So we went ahead and collected our data and analyzed the data. Last week we looked at descriptive statistics. So here you're essentially calculating the means and standard deviations if the data was normally distributed, or medians with interquartile range for data that is not normally distributed, your measures of frequency, proportion, so on and so forth. Then you subject them to a test. And this test is where you generate your p-value. And that p-value is what you compare against that significance level, and you make your statistical decision as to whether to reject or to fail to reject the null hypothesis. So we've looked at significance level. I'll skip over to the test statistic. What exactly is a test statistics or statistical tests? So statistical tests are described as they are mathematical procedures of obtaining data or statistics from the sample. Most of us would calculate these statistics using softwares. Softwares would be automated, but what goes on behind those softwares are a lot of complex mathematical computations. More often than not, we may not be aware, or if we are aware, then they may be too complex for us to even delve into. So we usually just look at the outputs from these statistical softwares like SPSS. But behind the scenes, what usually goes is a lot of complex mathematical computations. And this computation usually compares what is observed in the sample, that is the mean that we've seen in the sample, the mean blood pressure, compared to the expected if the null hypothesis were true. The reason why I'm stressing that is, remember, the whole concept of null hypothesis significance testing starts from the null hypothesis. We are starting from a point where we are saying there is no difference at all. And we are comparing no effect versus what you observe and trying to determine whether what we are observing is meaningful. Is it meaningful? But it's meaningful relative to no effect. That's why we are saying that statistical tests, what they're just doing is they're comparing what is observed in the sample, the small number of people you studied, vis-a-vis what you'd expect in the absence of any effect. That is what statistical tests do. So they look at the difference between what we calculate from the sample data versus what would be expected in the case that there was no effect, and tries to extrapolate that to the general population. The aim there is to answer the question, what we are seeing, is it due to an actual effect? Is it due to random chance, right? if the null hypothesis were true, if there was no effect at all, what is the probability of us getting that effect in the first place? That is what the statistical test is trying to answer. So at the end of it all, statistical tests gives us evidence, and that evidence is the p-value. And that p-value is what we countercheck against the alpha statistic to decide whether what we are observing meets that threshold to either reject or fail to reject a null hypothesis. So it's therefore important to remember that since statistical tests are key in deriving the observed values, the p-values, so on and so forth, then choosing a statistical test that is appropriate for that data is very important. So we'll also mention what things do you consider when you're choosing a statistical test? What factors influence the choice of a statistical test? One, it's a study question and objectives. A research question that seeks to compare efficacy of two drugs in terms of an outcome that is numeric, like mean blood pressure, would employ completely different statistical tests than if the study were a qualitative study where you're just looking at perhaps a quality of life as reported by the patient, for example. The design. If the aim of your study is just to describe what you're seeing in the sample and not necessarily to generalize it to the population, then you just stick to descriptive statistics. But if your design and your desire is to be able at the end of it all to try and make conclusions or generalize what you are seeing in that sample to the general population, then you choose or use a statistical test. So analytical studies would often employ statistical tests of either association or so on and so forth. The sample, very important, size of the sample. There are statistical tests that are appropriate for large sample size, but when you're dealing with small sample sizes that are more likely to be not normally distributed, then there are statistical tests that are specifically used in those scenarios. So sample is very important, not just the size, but also the representativeness of the sample. The data, what you obtain from the sample. The type and the summary statistic is important when choosing a statistical test. So numerical variables would be handled very different from other variables. Categorical variables would employ completely different statistical tests from numerical variables, for example. The distribution of the data is also very important. If you have data that is normally distributed, we often employ what we refer to as parametric tests. Parametric tests assume normality of distribution. It assumes that the data was normally distributed. If your data is not normally distributed, and we discussed last week how to check whether the data is distributed normally or not, then it is suggested that you use what we refer to as non-parametric tests. So the type of data and the distribution of data is very central in choosing an appropriate statistical test. The number of study groups is another important consideration. There are statistical tests that are utilized when you only have two groups. If you have more than two groups, then there are other statistical tests that will be more appropriate, and we shall look at examples of those. So in a nutshell, these are the key things that you'll be considering when you're choosing a statistical test. And the role of that statistical test would be to generate observed values and compare it with the threshold that we've set initially. So I'll give you a brief overview of some of the commonly utilized statistical tests. They may not be all of them, but just the most commonly used. We start with reminding ourselves the various types of data because this is very central. Often, categorical data and numerical data would have very different statistical tests. the various summary statistics, for example, mean and frequency. For example, when you're looking at a distributional, frequency analysis, they will also be handled very differently when it comes to statistical analysis. So those are the two key things I'll still repeat. Type of data and the summary statistics. And of course, from here, the distribution. Is it normally distributed or not normally distributed? So for continuous data, we have various types of statistical tests that we can use. So as you can see, our starting point is the type of data. Is it continuous or categorical data? Continuous data can be analyzed in various ways by considering the number of groups. Do we have two groups or more than two groups? In our current example, we want to compare placebo versus a new drug with regards to mean systolic blood pressure. So our outcome is a numerical variable. It's a continuous variable, mean blood pressure. It can occupy any value along the number line. How many groups do we have? We have two. So we have the group where they are taking the drug, and we have the group that is receiving the placebo. So it would fall under this category. Sometimes a study can compare three interventions. So you can have placebo, drug A, and drug B. Those will be more than two groups, so it will fall under this category. Now, having considered the type of data and the number of groups, the next thing you ask yourself, let's look at situations where you have two groups, and this is perhaps what most of us will use a lot. We ask ourselves, these two groups, are they related or are they independent? What is the difference? In this example that we are using, so we have one group that is receiving a drug, the new drug, and we have another group that is receiving placebo. These are two completely different groups of patients. Therefore, they will fall under the independent types of tests. However, if it were the same cohort of patients, say we have 30 patients, they're exposed to a placebo for a certain duration, then the blood pressures are measured. Then they are given a duration, what is usually referred to as a washout period, for the quote-unquote effects to wear off. Then they are exposed to a second intervention, which is now the new drug, and the blood pressure are measured. Then this will just be the same group, right? In as much as there are two different interventions, the data is related. We are just dealing with the same group, right? So you consider these two groups, are they independent or are they related? So say you wanted to compare the mean blood pressure between males and females, for example. Those will be two completely different groups. If you are to measure that blood pressure before and after an intervention in the same group, that will still be related groups because it's the same group, but data has been collected at different points. So that's the whole concept of whether the groups are independent or related. So if you have continuous data, an outcome that is continuous like mean systolic blood pressure, we have two groups. So we have a drug and a placebo group. Of course, that will be independent. Then these are the two tests that we can use. So we have what we call the independent student t-test. So independent student t-test is usually used to compare means between two different or two independent groups. However, I've put a slash there, the same for related, where we will use a paired t-test. The slash there is to cater for distribution of the data. If the data is normally distributed, we usually use the t-tests, either paired for related groups or independent t-tests for different groups. But if the data is not normally distributed, then we use Mann-Whitney and Wilcoxon tests. So This is what we refer to as parametric and non-parametric tests. So paired t-test is a parametric test because it assumes normality of distribution. It is utilized when you have data that is normally distributed. Sorry, the independent t-test. The paired t-tests and the independent t-test, sorry, both of them are parametric tests. The only difference is that paired t-test is used in related groups. Independent t-test is used in when the two groups are completely different. The non-parametric equivalent of the paired t-test is the Mann-Whitney. Mann-Whitney usually is used to compare means where you have two groups, but the data is not normally distributed. In scenarios where you have more than two groups, we commonly use analysis of variance, which is called ANOVA, or analysis of covariance, ANCOVA, and many other tests. So as you can see, the type of data, the number of groups, whether the groups are related or different, and whether the data is distributed normally or not normally distributed, those will guide you to choose an appropriate test. On the other hand, if you're dealing with categorical variables, again, we consider how many groups do we have? Is the data paired? Are the groups related or are they different? Right? And these will be the tests that can be used. So for independent groups, we often use chi-square statistic, but for situations where you have very small sample sizes, Fisher's exact test can be used. Where you have data that is paired for two groups, McNemar's test is what is usually recommended to be used. And for situations where you have more than two groups, then Cochrane Q test is what is normally utilized. So by far, the most commonly used statistical test is the independent t-test, the paired t-test, the chi-square, and the Fisher's exact. So these are the tests that you're more likely to use a lot. So the two t-tests and the chi-square stroke Fisher's exact. Analysis of variance can also rather sometimes is used a lot, but in situations where you have more than two groups. The other types of statistical tests, not for comparison, but to explain what we call explanatory analysis. A good example is regression analysis. The role of regression analysis is to explain what variables influence outcome. For example, say we have a situation where we are comparing the two drugs. I mean, the drug vis-a-vis the placebo, and we find that there is a difference. That difference could be due to the drug, but the difference could also be in the inherent characteristics of the study population. It could be that perhaps those who are put in the drug group are those who have better blood pressure control, they have better health-seeking behavior, they are more adherent to their therapy, and that's why the new drug appeared to have had a greater reduction or to cause a greater reduction in the mean systolic blood pressure. So how then do we account for these other potential issues that can affect the result? This is the role of regression. So we consider everything together, including the intervention. So we'll consider the age, we'll consider the sex of the patients, we'll consider the adherence level, we'll consider the initial resting blood pressure or other blood pressure at the time of entry into the study, and of course the intervention itself. And looking at all the five together, we distill which of those five are true influencers of the outcome. You might find that if you are to combine all the five, only the intervention comes out as the significant influence of the outcome. But sometimes you might find that there was a difference, but if you look at what influenced the difference, it was not really the drug. It was perhaps the distribution of the patients across the two groups. And that's the whole concept of sampling and ensuring that when you're drawing this individuals into the study, you do it in a manner that allows a large sample that are randomly drawn from the population so that the outcome that you get, the two groups are more or less comparable. So the role of regression analysis is just to account for potential confounders, any other thing that can influence the study outcome. So the importance of this regression analysis is that it not only tells us that there is a difference, it's also able to tell us the strength of the difference by giving us outputs such as the odds ratio. So you'll come across results talking about people who are taking drug A were twice as likely to have lower blood pressure compared to those who are taking placebo, so on and so forth. So it tells us the strength and the direction of the relationship between the things we are studying. This is a good example of a statistical test for explaining outcomes. So this study looks at risk factors for injuries of a certain nerve in the neck during surgery. So you have those who had injury to the nerve and those who didn't have injury to the nerve, and you compare the two. What were the differences between the two groups? And you distill the ones that will remain as independent influencers of outcome, as in standalone, they influence risk of injury. And here they found that if you have to compare, if you have to take into account everything, those who had benign thyroid, for example, they're talking about independent risk factors for the nerve injury, were one, those who had intrathoracic goiter, those who had reduced surgery, those who had total lobectomy. So there are many other things that were considered, but considering everything else, only these ones remained as significant influencers of outcomes. This is what is referred to as regression analysis or explanatory analysis. A bit complex, but it's something that we need to keep in mind. The other one is correlation. Correlation usually is used for continuous variable. Essentially, it talks about how change in one variable influences the other. For example, here they are looking at, does duration of surgery influence operative blood loss? So the trend here generally is that the longer the duration of surgery, the higher the degree of intraop blood loss, for example. This is what is referred to as correlation. Those are the tests that you can use to compute the observed values. So we started with a research topic, research question. We formulated our hypothesis. We chose an alpha value or a significance level. We collected the data, we analyzed, and we came up with a test statistics. So let's look at test statistics. What are they? To help us with that, we will still use this case where we have two groups, group being given a drug and a group being given a placebo, and we have their values here. Our hypothesis initially was that the new drug reduces the systolic blood pressure compared to placebo. Our null hypothesis was that the new drug, there is no significant difference in the mean systolic blood pressure of those taking the new drug vis-a-vis those who are taking the placebo. That was our null hypothesis. So we went ahead and we collected the results. To help us with that, let me try and demonstrate briefly. I know Samuel will handle the practical aspects, but let's just use this case to look at how statistical tests can be used to compute the observed values, and then how we interpret the observed values against the thresholds that we set. So to enable us to do that, we will use this case where our outcome is a numerical variable. That numerical variable is mean systolic blood pressure. We have two groups, which is a group taking the antihypertensive and a group taking the placebo. So we ask ourselves, we've set a significance level or alpha level of 0.05. That is our threshold. to use to reject or to fail to reject the null hypothesis. What we need to do is to compute that p-value, then we will compare it against um, um, well, then we compare it against the threshold. The slides are not visible because I want to share SPSS and demonstrate to you using that mean systolic blood pressure as an example. So let me share my entire screen. So I can share the entire screen. Can confirm that you can see my entire screen.
Okay, I
Right.
can see it, Doc. I can see it.
So all right, thank you. So let me go to SPSS. So remember, we agreed this is the view that you'll get, data view and variable view. I already have my data, so I'm going to just import the data. It's in the form of CSV. So I'm going to just load it. Uh, just click OK. Uh, Perfect. So this is the data. So I don't need this. So in the variable view, I have three variables. So I have the ID. So this is the patient ID, which is a numerical. I have the group. So the group here is either drug or placebo. So I've put it as a string, but usually it's easier if you code into 0, 1 or 1, 2, and I'll show you why it's important to do so. And then our outcome, which is a systolic blood pressure, is a numerical outcome. So if you go to the data, this is how it looks like. So we have 30 patients who are taking the drug, and these are their mean these are their systolic blood pressure. And we also have 30 patients who are taking the placebo, and these are their blood pressures that were taken. Now, what do we want to do? We want to compare this mean blood pressure between these two groups, the drug group and the placebo group. Remember, we are dealing with numerical data between two groups. So someone to suggest for us an appropriate statistical test to use. So who wants to suggest for us an appropriate statistical test to use based on the previous slides? Which test do you think would be useful in this case? So we have continuous data, two groups. What else do we consider? What else do you want to know before we choose a statistical test to use? So, UNITA, you're saying independent t-test. So you've already concluded that we are going to have data that is normally distributed, but we'll need to determine that because we are at a point where we have just two information. We have continuous data for two groups. Now, these two groups, are they paired or not paired? They are completely different groups, right? So we have drug group and placebo group. So they are independent groups. So we can either use the independent t-test or we can use the Mann-Whitney test. The difference would come in the sense that if the data is normally distributed, then we use the independent t-test. If the data is not normally distributed, then we use the Mann-Whitney test. So let's determine whether our data is normally distributed or not. So remember, we agreed that how do we check? You can either use visual or graphical methods by looking at histograms or box plots, or you can use statistical tests. So let's do that. So usually you go to analyze, and then descriptive statistics. You go to explore. So we want to explore systolic blood pressure. Um, so what do we need? We need the descriptives. Then under plots, remember to tick histogram. You don't really need the stem and leaf. Histogram will enable you to get a visual inspection, a graphical method of looking at data, whether it's normally distributed or not. Once you tick the normality plots, then it will compute for you using either the Shapiro-Wilk, depending on the sample size, or the Kolmogorov, the difficult one. Here you click to display both statistics and plots. So it's computing, and here we have it. So we have 60 participants. The mean blood pressure for the 60 participants is 131, with a standard deviation of 10.9. The median is 132. The interquartile range is 18.5. But is this data distributed normally or not? Let's look at the histogram. We agreed that normally distributed data in the histogram usually assume a bell curve kind of distribution. So if you double click on the histogram and you go to elements and you add the distribution curve, which is the line of best fit, essentially shows you that, then you can see that the superimposed line actually assumes a very nice bell curve and suggests that the data could be normally distributed. But we agreed that graphical methods can sometimes be a bit subjective. So someone else can look at this and be like, oh, on this side, this one has gone a bit higher than this, so could it be normally distributed or not? In the case where you're not too sure, we agreed that the other graphical method is a box plots. And what do we look at here? We agreed that the upper edge of this box is the 75th percentile, the lower edge is the 25th percentile. The dark line here is the median. So is the median midway between the two percentiles? What we have here on top and below, these are the extreme values, the range, the lowest and the highest. So this lowest highest, if they're equidistant from the mean, from the median is it equidistant from the percentiles, then you can say that it looks like it could be normally distributed. But again, someone could say that this distance is slightly longer than this distance. So again, graphs can be a bit subjective. So is there a more objective way of looking at whether the data is distributed normally or not? Yes. So we agreed that we have these two tests, Shapiro-Wilk and this Manov test. We utilize Shapiro-Wilk usually when you have small sample sizes, usually less than 30, but some people describe up to 2,000. But SPSS usually does both of them. What you check for is this significance. If P is less than 0.05, yeah, if that P is less than 0.05, usually it tells you that the distribution you are seeing is actually not normally distributed, right? So usually if P is greater than 0.05, it tells you that the distribution you are seeing is not any different from a normal distribution, and therefore you conclude that that data is normally distributed. So considering what we've seen, we have continuous outcome, two groups that are independent, and the data is normally distributed. Then we settle for independent student t-test as our statistical test of choice. So then we go ahead and compare the mean blood pressure using that statistical test. So usually, again, you go to analyze and you compare the means. We are using the independent sample t-test because we've agreed based on the criteria that this would be the most appropriate test to use. We want to compare systolic blood pressure, but we want to compare between two groups. So this will be the grouping variable. We define our groups. So we have the drug group. Sorry, let me use. So we have the drug group and you have the placebo group. Now, the importance of coding is that if we had coded our data into 1 and 2 or 0 to 1, it would be very easy to put 0 and 1 here. The problem with this, if there's even a typo here, then you'll not get your result. These wordings here have to be exactly what is in these groups here. Anyway, you define your groups. You go to options. You want to use a confidence interval of 95%. Confidence interval is essentially derived from the alpha value. It's 1 minus the alpha value. So alpha value was 5%. So the confidence interval will be 95%. and want to get estimate of the effect size, and we shall look at what effect size is. You click OK. Once you do that, then you get such an output. So we've compared the systolic blood pressure between the drug group and the placebo group. There were 30 participants in the drug group. There were 30 participants in the placebo group. The mean blood pressure in the drug group was 127 with a standard deviation of 9.5. And in the placebo group, it was 136 with a standard deviation of 10.2. This is statistics, what we get or compute from the sample. What else do we get when you compute statistical, when you're computing these statistics using statistical test? You get such a table. This is a result output, and we shall look at what each means and how it helps us in null hypothesis significance testing. What we need is this significance level here, not this one, sorry, this significance level here. And this is what most researchers would run to look at. But there are other components here that are far more important than the p-value, which is what is put here, significance. So let's look at, so that's how you would run a statistical test, for example. I've just used mean blood pressure. I've demonstrated how to do a comparison of mean when you have two groups that are independent, not related, and the data is normally distributed. Samuel will demonstrate the rest during the practical support session. The reason why I did this is so that we now look at the output. How then do we conclude whether we are rejecting or not rejecting the null hypothesis? So we'll go back to our case. So remember, we started with a research topic, we had a research question, we had an hypothesis, we've collected the data, and we have the outputs. So I've just copied this output from the SPSS, exactly what we got from the SPSS. What are the components of the test output? First is a summary statistic. Here, the summary statistic, we have measures of central tendency, which is mean for both groups, and measures of dispersion, which is standard deviation. So for each group, we have a mean and standard deviation of the systolic blood pressure. And we understand what that is. More importantly, we have something called effect size. What is effect size? Effect size essentially is a quantitative measure of the magnitude of the difference between the two groups. What is the magnitude of the difference in the mean blood pressure between the two groups? So we will conclude that group 1, which took the drug, had less systolic or lower systolic blood pressure compared to those who took placebo. But what is the magnitude of that difference? It is what we are seeing here, mean difference, negative 9.5. It means that those who are taking the drug had lower mean systolic blood pressure. And the difference between the two groups was 9.5 millimeters of mercury. This is what we call the effect size. And very important when you'll be looking at interpretation of the p-value. What is the other output of the test? We have what we call the confidence interval. If you look at this, we not only have the mean difference, but we have the 95% confidence interval of the mean difference. And we've been given two. Usually you are given the upper level and the lower level. So here we have negative 14 and negative 4.4. What does that mean? Confidence interval essentially means the range of values in the general population that likely contains the true population parameter. What do we mean? We started with a population. We couldn't study the whole population. So we drew a sample that is representative of the whole population. We then set our hypothesis, went ahead and collected data, analyzed. Now we have statistics. Here we have an effect size, and here we have a mean difference of 9.5. The 95% confidence interval tells us that if this study were to be performed in the population from which this sample was drawn, the mean difference in the population, which is the parameter, not the statistic, is likely to lie between negative 4.4 to 14. That is what confidence interval means. Another way of putting the confidence interval is if you are to do this study many times, if you are to do this study many times, if you are to draw many samples from this single population and you do exactly the same study many times, 95% of this calculated confidence interval would contain the true value, the true population parameter. Those are two ways of looking at confidence interval. Most people would go with the initial view, but both of them, they are talking about the same thing, but different ways of looking at it. Why is confidence interval important? Is it can be used as a surrogate marker of significance. Let's look at this graph over here. In our case, we got a mean difference of negative 9. The reason why there is a negative there is because we are looking at the new drug relative to placebo. So therefore, patients who are using the new drug have a lower blood pressure. So that's why you're seeing this negative here. But the 95% confidence interval is from negative 4, negative 14 to negative 4. So all of them are on the same side of the number line. Now this line here represents 0. 0 is often named or is often called as the line of no effect, as in 0 would mean there is no mean difference between the two groups. There's no difference in the blood pressure between the two groups. That is what this line means. This line, on the other hand, the red and the dark blue represents confidence interval. The dark spots represents the extents of the confidence interval, the lower and the upper bound. How do we interpret confidence interval? If the confidence interval, both the upper and the lower bounds are on the same side of the number line, they don't cross the 0. Often the results would be considered significant because either way there was a mean difference between the two groups. As in, at no point did we get a 0. At no point did we cross over to the other side where actually those who were taking the drug had a higher blood pressure compared to placebo. So long as the extents of the confidence interval are on either side of the NAND value and they don't cross the 0, we consider the results as significant. In this case, negative 14 to negative 4, they are still on the same side of the number line. They have not crossed 0. But if the confidence interval extended from negative 14 to positive 5, it would look like this. So we've crossed over to a point where there was no significant difference between the two groups to the point where the result is actually the opposite. So often, if the confidence interval crosses 0, the results will be considered as being not significant. This is the reason why sometimes confidence interval is used as a surrogate marker of significance and can be used in place of the p-value. That is one of the other outputs of the statistical test. This is probably the most popular and what most people would go with and overlook the rest of the outputs, the p-value. And we agreed that the p-value is the probability of observing the data or observing the current result when indeed there was no difference, when the null hypothesis was true. Because remember, we agreed that p-value usually assume that the null hypothesis is true. So in this case, we got a p-value of less than 0.001. What is the conventional interpretation of this? Most people would look at it this way. There is a category of researchers who would say that since that p-value is less than the alpha that we set, which was 0.05, the results are statistically significant, which is fair. Some would go as far as to say that these results are highly statistically significant because it's actually less than 0.05 by quite a large degree. Do you think that's a correct interpretation of that? Anyone? Would you think that is an accurate interpretation of that p-value? That the results are not only significant because they are less than the alpha, but they're highly statistically significant because it's actually 0.001, which is, less than exactly half the threshold that we set. Do you think that's a correct interpretation? As you think about that, another school of thought, and often you'll come across this, since we defined p-value as the probability of seeing a difference when there is actually no difference at all, and p-values are actually probability values. They're supposed to be expressed in terms of probability. So if you had to convert 0.001 into a percentage, then someone would say there is a 0.1% chance that the null hypothesis is true, that there is a 0.1% chance that there is no difference, and therefore the results are significant because the chance of there being no difference is very small. What do you think about those two statements? Do you think they are accurate interpretations of the p-value? Because this is exactly what you come across in most literature. So Derek says it's not true since p-value does not estimate significance. So it's a very good point. We agreed that p-values are threshold. They don't give us or quantify the magnitude of the difference. So therefore, it does not matter whether p-value was 0.00001 or if the p-value is 0.049. The point was it's less than the threshold that was set. So either way, the result would be considered significant and the null hypothesis would be rejected. What about the second point, that there's a 0.1% chance that the null hypothesis is true, that there's a 0.1% chance that there is no difference? What do you think about that interpretation? Because that's another interpretation that is there in literature. I think that may be a bit more difficult to answer, and I'll help you answer that in the subsequent slide. But either way, both are not accurate interpretations. So what does p-value mean? Assuming you had the same study, but the p was 0.05, would you consider this result as significant or not? So someone is saying it's not a quantifying test since it's just a threshold, hence that interpretation is dangerous. P-value should just be interpreted as is. Okay. Question is, what if the output p-value was 0.05? I mean, it's exactly the same level as the alpha or the threshold. Not more, not less. Exactly the same. Would you consider these results as significant or not? Anyone? These are some of the fundamental issues with the p-value. Because remember, the origin of the p-value was rather arbitrary. It was just a threshold set by Fisher in 1934. Should we then continue to conform to this? Assuming you got a p-value of 0.049, someone else gets a p-value of 0.051. The difference is very small, 0.002. Yet, we would declare the one with 0.049 as significant and completely throw away the results when the p-value is 0.051 or 0.052. These are some of the fundamental issues with the p-value. Either way, this is how it's correctly interpreted. Remember, we agreed that p-value is usually computed assuming that the null hypothesis is true, that we are starting from a point where we are assuming there is no effect. Then we are comparing no effect with what you observe and trying to determine whether what you observe is actually meaningful in the first place. So therefore, if you get a p-value of 0.001, what it just tells you is, in the case where the drug truly has no effect, in the case where the null hypothesis is true, there is actually no effect, then we would see a difference, the same as ours, or even more extreme, only 0.1% of the time. So it just tells us, assuming the null hypothesis is true, what is the probability of us getting a result the same as what we are getting? It does not tell us what is the probability of the null hypothesis being true. And that is the distinction I want us to get. So what are the misinterpretations of p-values? One, most people would say that p-value indicates strength and magnitude of an effect. That is entirely not true because we've just seen that p-value are mere compared against a threshold. If you want to quantify the magnitude of the difference, then use effect size. In the case that we saw, the effect size there was the mean difference between the two groups. And we saw that the difference was actually 9.5 millimeters of mercury. P-value does not tell us in any way that difference. It just tells us that what you observed was less than the threshold we set. So the results are significant, but does not tell us what was the magnitude of the difference between the two groups. If you want to determine that, use effect size. Not just effect size, but effect size together with its confidence interval. Another misinterpretation of p-value is that it is the probability of null hypothesis being true, as in it is the probability of you not getting a result, probability of there not being an effect in the first place. And most people would say, since that probability is very small, then our results are significant. That is entirely not true because we've agreed that what we are saying is that p-value is a probability of an observation versus null. We are starting from the point where we are assuming there is no effect. It's not the probability of null given an observation. So most people interpret the p-value using the second part of the statement, while in real sense, p-value is just what is the probability of us seeing the effect when there is actually none. Okay, so it's not the probability of the null hypothesis being true. If you want to quantify whether or not the null hypothesis is true, the probability of that, what is recommended is a completely different framework of hypothesis testing. This is what is referred to as Bayesian statistics, quite a complex one. So therefore, we limit ourselves to just talking about probability of an observation given the null. If you wanted to talk about probability of the null, then we use a completely different framework and not the null hypothesis significance testing. The other misinterpretation of the p-value is that p-value is the probability of that the result occurred by chance. So if it's less than the alpha, then it's less likely to have occurred by chance. What we need to appreciate is that it tells us, p-value essentially tells us what is the probability of us getting the result when there is actually none. But it does not tell us the source of that result when there is actually no difference. The source of that result could be the random error, sampling error, could be by chance, could be due to an actual true effect. P-value in no way tells us the source of that result. So therefore, we cannot be able to quantify this chance that we are talking about here. What it just tells us is what are the chances of us getting this result when actually there is none in the first place. There is no difference in the first place. The criticism against p-values are the following. One, it's heavily dependent on sample size. Most of our studies would involve small sample sizes, 10, 20, 30. The smaller the sample size, the less likely we are to determine subtle differences between groups. So therefore, studies that use large sample sizes, whole population studies like in Scandinavian countries where they're able to do studies on their entire population, they can be able to detect even the slightest and trivial effects. However, in situations where you study very small sample sizes, you can miss subtle differences between groups. And therefore, you might end up with non-significant p-values. Not that there was no difference in the first place, but because of the nature of the sample, the size and the representativeness of that sample. And that's one of the criticism against p-value. It's largely influenced by sample size. So if you get a p-value of less than 0.01, but you studied only 5 participants, someone would take that with a pinch of salt. But if you get a p of 0.049 or 0.051, but you studied the whole population, then someone would consider those results with um, uh, quite high level of certainty compared to yours. So what is recommended, since it's heavily dependent on sample size, don't just look at the p-value. Consider the effect size, the actual difference between the two groups, and the confidence interval. Because you might realize that in as much as the p-value may not be significant, may not meet that threshold, in the clinical scenario, does that difference mean something clinically? And this is very important because in studies like in cardiology, a difference in mean blood pressure of 10 millimeters of mercury could mean a difference between you getting a stroke or not getting a stroke. So in as much as p-value may tell you that the difference is not significant, look at the biology of what you're studying. Does that 9 millimeters mean something clinically? Okay. The other issue with p-value is that it's known to encourage what is commonly referred to as p-hacking because most of us have this fear that if you don't get significant results, then your study is worthless. So you torture the data till you end up with a p-value that is significant. That is what is referred to as p-hacking. So you manipulate the data, you leave out some participants, you report selectively, you do all manner of things to achieve a p of less than 0.05 because you think that your results then would have meaning. And this is what has been cited as one of the major issues around p-value. So you'll find that the credibility of most research that is published is thrown into question. Okay. The other thing is that researchers would often think that journals are more likely to favor and accept papers that are reporting quote unquote significant results. Um, and that may be true. What that means is that we then end up with a situation referred to as publication bias. So the results that are more likely to get into them to literature are those that are considered significant. However, those that were not significant but could have been useful elsewhere don't really get to literature. So therefore, we undermine reproducibility of results or research, and also trust in research findings. The other issue is, since we are so drilled into trying to determine whether the results was significant or not, based on whether the p-value that we saw is greater than or less than the threshold, we often end up with a mindset where we dichotomize outcome as to whether it was significant or not significant, overlooking the significance of those results or clinical relevance of those results in the first place. And you might miss very important findings. And this is the whole point of clinical vis-a-vis statistical significance. And I'll illustrate that in the next few slides. So what is recommended? One, don't use P of less than 0.05, that cutoff or alpha level of 0.05 as the magic cutoff point, because we've looked at the historical context of where that P of 0.05 was derived from. We've looked at what p-value means in the first place. It just tells us what is the probability of us seeing the result when there was none in the first place due to many reasons, either random variation, chance, sampling error, amongst others, right? So therefore, this 0.05 cutoff should not be used as a textbook or rather magic cutoff. What is recommended is that consider the effect size, not just the p-value, okay? Because small p-value does not necessarily mean that the results are highly significant, that it's the ultimate proof that the results you've gotten are the truth, right? So therefore, it's always important to report effect size and confidence interval. In fact, most journals nowadays encourage reporting of effect size and confidence interval rather than the p-values. So if you go online, for example, they mandated authors who are submitting papers to them to discard p-value in their papers and just report effect sizes and confidence interval. And we've looked at what effect sizes are and how to interpret the confidence intervals. The reason for that is so that you're not just looking at the dichotomy of outcome, significant or not significant. You're also considering the magnitude, the direction, and the meaning of the result that you're getting. Let's consider this. Say you had a mean difference of -2 in the study we just looked at, but with a p-value of 0.01. We have a mean difference. The p is less than the alpha. So we would consider this to be significant, right? It's statistically significant because it's less than the alpha. But what does 2 millimeters of mercury a reduction in blood pressure mean in terms of risk of stroke or MI? Does it really translate to clinically meaningful outcome, right? Consider another scenario where you had a mean difference of -10. So the patients who are taking the new drug had a reduction of blood pressure by about 10 millimeters of mercury relative to placebo, but the p-value of 0.08. So it was not statistically significant, probably because it was a small sample size, there were issues of sampling, so on and so forth. But if you are to look at that 10 millimeters of mercury reduction, what does that mean in terms of cardiovascular event? Then it would mean something. So in as much as the p-value is not significant statistically, the effect size could be important clinically. And this is the whole point of statistical vis-a-vis clinical significance. So statistical significance based on p-values and confidence interval, purely mathematical computation. Clinical significance looks at not only the computed effect size, but what is the meaning of that effect size in terms of practice, okay? So it looks at real-world impact of what you're seeing. And essentially, this is what is recommended to be utilized. So don't just fixate on the p-values, whether it's less than 0.05. Look at the effect size. What was the mean difference, for example? What does that mean difference mean in terms of what I'm studying? I'm looking at a reduction in blood pressure, but my aim is to reduce mortality, to reduce the risk of cardiovascular events such as strokes and MI. So therefore, 10 millimeters of mercury, as much as the p-value was not less than 0.05 to me and to the patients, it's going to translate to meaningful clinical outcomes. And therefore, those results, in as much as they are statistically insignificant, clinically, they will be considered significant. The other recommendation is to interpret in context. So don't just look at the p-values. We've agreed that the p-values may be influenced by many things, including the sample size. So consider the sample size. Consider evidence prior to what you have. You might find that all along there was evidence to suggest a difference, but you yourself, you found no difference, right? So then you have to interpret your findings in context of what others have already found and try to explain why your results are deviating away from previous individuals. Be transparent. Transparency means that at the point of coming up with a study, define and specify things appropriately. Define your research question. State and specify your hypothesis. Specify your plan for analysis. Specify your significance threshold so that at the end of it all, it becomes something that was set before the study is conducted and not an afterthought. Report all results. Negative results or absence of effect size is also a result. Absence of an effect size, when you find that there was no difference between the two groups, it's still a result because it means that maybe the intervention does not work. Consider alternatives, and these are the other frameworks different from null hypothesis significance testing. And I'd invite you to, in your own free time, look at these other approaches. Perhaps after you've considered and went through null hypothesis significance testing a couple of times and gotten the gist of it, you can, in your own time, consider these other methods. They have been suggested as more superior methods to null hypothesis significance testing in certain contexts. They may be more complex in terms of how they are computed, how they are interpreted, but at the end of it all, they are going to enrich your understanding and also some interpretation of statistical outputs. I'd also invite you to look at this paper by the American Statistical Association's statement on p-values, the context, the process and purpose of p-values, evidence for and evidence against the p-value, and the recommendations as to how to proceed given the current limitations of the p-value. I know it's been a long talk. I hope I've been able to at least give you a few points here and there as to what exactly null hypothesis significance testing is. I've chose to introduce you to the controversies so at least even as you start off, you be aware as to what are the pitfalls during interpretation of the p-values are and what are the recommended best practices in reporting these p-values. I hope this has been of help to you. It's unlikely that from just this one presentation, we are all going to understand everything about null hypothesis significance testing. So what I'd encourage you is repeated exposure of this content in various forms, either rewatching the recording or reading material that I'm going to share through Samuel. And then in case of any questions, always feel free to reach out for further clarifications and discussion. I thank you for your time. Over